hi everyone, and thanks so much to the organizers for giving me the opportunity to present in this seminar series. And what I wanted to share with you today is some work that my co-authors and I have been doing in the Malawi Rift, in particular looking at faulting patterns in the North Basin of this rift. And in a way, it's a classic half graben, and it looks very simple compared to many rift systems. So maybe it's a nice point of comparison for other places. So some of the questions that I hope to tackle today are basic ones and are not new, but those are, how is strain distributed between the border fault and intra-rift faults, and have a little cartoon here at the bottom of a half graben basin with the oh, here's my mouse, with the border fault and these intra-rift faults happening within the hanging wall. And then the second question I hope to tackle is what controls along strike variations in these faulting patterns. And to think about this, I'm going to take you to the southern part of the East Africa Rift system. Here's the Malawi Nyasa Rift. This is in a part of the East Africa Rift system that's experienced less total extension. It's at an earlier phase in its development. It's a very fault-dominated system, like a lot of the rift basins along the western rift of the East Africa rift system. And so now we're going to zoom in here to the Malawi Rift. And so the Lake Malawi sits right here in the heart of the rift. It's one of the largest freshwater lakes in the world. And you can even already just see from the bathymetry in the lake and the topography on shore, kind of the overall configuration of this rift. We have these large border fault bound basins. These border faults are really large. They're over 100 kilometers long. And you can see deepening bathymetry towards these border faults. And the polarity of the basins switches along strike. So we have a border fault bounding the eastern part of the North Basin here. And then as we go south in the Central Basin, the border fault is now on the western side of the rift. But we're really going to focus here on this in this northern basin. And from data that's been collected here over the years, we already know that, again, that we have these border fault bound basins where both the water depth and the sediment thickness is thickening towards these large faults. And if you stand here on the western side of Lake Malawi and look to the east, this is the view that you see. These are the Livingstone Mountains, and they're just this spectacular mountain range soaring 2 kilometers above the lake. So this is a really very, very beautiful rift system. And it's a very nice one to kind of try to address some of the questions I laid out to you before. As I tried to show you, we have these very large border faults, and we know that from the longer earthquake history that these are thought to host relatively large and deep earthquakes. But we also see earthquakes occurring on faults within the rift, these intra-rift faults. And that's kind of exemplified by an earthquake series that happened here in 2009 near Karanga here in northern Malawi on the western side of the lake, where a series of earthquakes between magnitude 5.5 and 6 occurred on one or more faults that are here in the hanging wall. And so this sets up a nice environment in which to examine patterns of faulting. And to do that, we're going to use some data from the segment experiment, and which had many different components, which are shown in the map here. Collecting these data and analyzing them has involved a large team of US, African, Malawian, and Tanzanian scientists. It included a broadband onshore, offshore experiment, magnetotelluric data, geochemical sampling, a geodetic network, which actually with some of the members of this team is still operating, and an active source seismic imaging survey within the lake, which is shown with all these curly red lines and the circles, which are lake bottom seismometers. And so I encourage you to look at many of the exciting results that have come from this project, but today we're really going to focus on the active source imaging of fault systems within the lake, and in particular focus here on the North Basin. And so I should say that acquiring these data was quite an adventure for a marine scientist who's accustomed to collecting data on dedicated specialized research vessels offshore. We used ships of opportunity to acquire these data, and those are shown here. These are ships that are based within Lake Malawi, and were kind of repurposed for a marine geophysical experiment. All right, so I'm going to in particular focus on two types of data which provide us with complementary information on rift structure. The first are seismic reflection data, and an example of those data is shown here. This is again across the North Basin, and hopefully just to get your eye in, we're looking sort of at a cross section through the earth. This is the seafloor, and hopefully you can see all of these layered reflections. These are sediments within the basin. And hopefully you can also see, even at this scale, some offsets on those sediments. And these are the Intrarift faults. And the whole sediment package is thickening to the east against the border fault. And then the other type of data that we'll employ are seismic refraction data that were acquired on those lake bottom seismometers. And those can be used to give velocity models of the sediments and the crust. And so this lower panel is showing us a slice through a 3D seismic velocity model along the same profile. And so we can see that the slower velocities are showing us the sediments, and those are in the blues and greens. And then the yellow are showing us crustal velocities. And we can see that same basic geometry being recovered by the 3D velocity model, with this thickening sediments to the east and some rift blocks within the basin. And because the sediments are really quite thick here, in excess of 5 kilometers, the refraction data were really important to constrain seismic velocities and thicknesses, since our seismic reflection data were necessarily acquired with a relatively short streamer, and so it has sort of limited velocity constraints with depth. And so we can kind of combine these to develop models of the thickness of sediments and locations of faults. And so on the right-hand side is showing a nice paper from my collaborator, Christopher Schultz, that's showing both the thickness of the sediments and faults across the whole of Lake Malawi from a combination of segment data and some existing legacy data. But as I said, we're going to zoom in here on the North Basin. And so if we want to think about the distribution of extension between the border fault and intra-rift faults, the first thing we need to do is actually try to constrain the total extension that has occurred on the border fault and intra-rift fault. So first we'll take the border fault, the Livingstone border fault. And again, what I'm showing here are results from a 3D P-wave velocity model from Natalie Accardo. And the left-hand panels here are showing us like two cross sections through this 3D velocity model. And the middle panel is showing us a depth slice at 4 kilometers through this model. And again, the sediments are shown as these lower velocities, which are primarily in this color scale in blues to purple. And you can see the thickening sediments towards the Livingstone fault. And yeah, as we go into the central basin, the polarity reverses and sediments now thicken to the west against the Nyasa fault. But using this model, we can constrain the thickness of sediments that are within this basin, and use those together with the elevation of the Livingstone fault to look at the kind of total vertical offset on that fault and estimate the total throw on that fault. And that's what's being shown here. So the upper panel on the left is showing us just elevation onshore, and the kind of the black lines are sort of a smooth fit to the highs of that elevation. Of course, there's been erosion of the uplifted footwall, so this is sort of a minimum estimate in a way, but we've sort of taken the highest topography as our best shot. And then the middle panel is showing the depth to the base of the sediments estimated from this velocity model, and then this is the total vertical offset. And so kind of combined, they give total vertical offsets on the fault of 7 or more kilometers. And depending on the dip that's assumed, that gives a throw of at least 8 kilometers. And so So you have these these are, as we know, very large border faults, and now we have even better constraints on just how much throw has occurred on those. And so our next step is now to characterize the amount of faulting within the basin on these intra-rift faults. And so here I'm showing you 3 seismic reflection profiles across the North Basin, overlain on velocities extracted from that 3D model. And what you can observe there are some very prominent faults here within the basin. Some of them have throws of in excess of, or vertical offsets, I'm sorry, of in excess of 2 kilometers. And so what's shown on the right is
Donna?
Yes?
You've now used 10 minutes.
Yeah, thank you very much. And is on the right-hand side here is an updated fault map of this basin. And these circles are showing the vertical offset estimated on these intra-rift faults. And you can see that, yeah, the largest circles are, over 2 kilometers. And so now one question we have is, okay, how much do these intra-rift faults, as big as they are, contribute to basin opening? Because, I mean, the border fault is gigantic, right? And so, and there's 2 possible origins or contributions to this intra-rift faulting. One is that they're actually helping to contribute to the opening of the rift. But the second one is that they're actually a response of flexure of the hanging wall. The hanging wall is bending a lot towards the Livingstone fault. And so we compare the extension that we observe with what we would expect just for that flexure based on the shape of the overall shape of the hanging wall. And we find that that flexural component can only account for about 40 to 70% of the extension. And so then if we take the remainder of the intra-rift faulting and we compare that with the border fault, we estimate that these intra-rift faults have accommodated about 20 to 25% of the cumulative opening. And so they are in fact playing a role. And it's interesting to compare along the rift and see that the amount of extension that we estimate that these intra-rift faults are accommodating in Malawi is less than what's observed farther north in the Tanganyika Rift, but more than what's observed in southern Malawi. And so I kind of offer a couple possible explanations for this, but of course that's going to await further work. And then to come to my second question was along strike changes in faulting pattern. And so now what I'm showing you is kind of a look on the right panel is a look along the rift, comparing the vertical offset on the border fault, which is this dark dashed line here, with the cumulative extension happening on the intra-rift faults. And so the individual ones are in colors, but then if we sum them all up, that's in this dark black line. And we can see pretty interestingly that in the south, a larger proportion of extensions happening on the border fault, whereas in the north, more of it is happening on these intra-rift faults. And there's a couple possible explanations for that. One is that a change in the orientation of pre-existing structures. Some of Fola's earlier work has used magnetic data to characterize the pre-rift structures, and we see this kind of rotation to a set of structures that are more oblique to the rift, where he showed that you also had more kind of broken up and segmented rift faults, and so perhaps that contributes to a larger amount of inter-rift faulting and less displacements on the border fault. Another possible explanation is that we have a change in the orientation of the basin along strike, where perhaps it's a little bit more oblique in the north and the south. And so that might be another contribution. And then my final quick point is that, so far I've just focused on cumulative rifting fault patterns and changes in those along strike. But another interesting thing we can have from these data is a look at which of these inter-rift faults are active. And so if we zoom in and look at the very shallowest sediments, I'm going to go to the next slide and just zoom in on this upper panel. Here's the lake floor, and then we see a really prominent reflection below the lake bottom, and that was formed during a mega drought about 75,000 years ago, when there was a huge reduction in lake levels. And you can see that pretty much every one of these inter-rift faults is offsetting that mega drought reflection, implying that all of these faults have been quite recently active. And that's consistent with work from Cindy Ebinger and her co-authors looking at seismicity within this rift from the segment experiment, which also shows numerous earthquakes occurring on these intra-rift faults. And so with that, I'll leave you with my conclusions. I'm sorry if I went a little bit long there.
Thank you, Donna. We have time for one question. Is there any question for Donna?
There's a question in the chat.
Oh, okay. Let's see. Okay, so Robert Winch, I'm sorry if I'm not pronouncing that properly, is asking, do I infer correctly that the sequence of faulting is younger to the east?
I have not looked into that in detail yet. It's true, the faults on the oh, sorry. So let me it's a more nuanced answer, I guess. There are a couple of faults that are farther east that actually seem to break the footwalls of the larger intra-rift faults that seem to have small cumulative offsets, but a lot of recent offsets. And so we do see some kind of variation within the lake where it's not that the faults with the largest cumulative offsets always have the largest recent offsets. There's some faults that have little cumulative offset, but have a lot of recent offset. And one of the most prominent of those is in the kind of eastern side of the lake, close to the border fault, which has a beautiful little channel associated with it on the lake floor. So sorry I didn't answer that very clearly, but I hope that tackles your question partially.
Thank you, Donna. You have more questions coming in the chat, so you can
I can address them there. Thank you.
Awesome.